Welcome to the second video on charging and discharging capacitors. Let's get right into it. So to charge up a capacitor, we have a circuit here with a battery, and we have our capacitor, and in this case we've got a bulb as well. So we connect these up, electrons flow, they end up piling up on this side. This side becomes positive, it forces electrons, well these electrons on the side force away electrons still through the bulb and around to the other side of the battery. It doesn't happen instantaneously. Electrons build up on the side over time, and that's what we call discharging, the fact that it happens over an amount of time. And we're going to see that actually happening in real life in a second. And discharging is when we take the battery out, so there's no more battery here anymore, and we disconnect the capacitor, which has already been charged up with lots of negatives, to this bulb, and we connect this up. What happens is the electrons flow around because they're attracted to these positives on this side. They flow around, they flow through the bulb. And again, that doesn't happen instantaneously. It happens over a period of time. It depends on the capacitor, it depends on the bulb, but it can happen over a time of a few seconds, or it can happen over a time of a few minutes or even longer. So that's your charging, your discharging your capacitor. So let's see if we can get this video of this working. So I'll just let it load up. So this is going to be a video of the same thing. There's a lot of wires there, but the wires, the circuit is just the same. They've got this charging capaciting circuit, capacitor circuit. So there's a bulb and a battery and a capacitor. And we'll watch that one first. So they connect it up. They're going to flick the switch, and in the corner you've got a picture of the bulb. It starts off bright and it gets less and less and less. So that was this top circuit here. That was this one over here. The bulb started off bright, and as the capacitor charged up, the bulb got less and less and less. Now they're going to switch it so that they take the battery out, and all of that charge is going to flow around the bulb. And again, it takes in this case about 2 or 3 seconds to do that. So let's see that. They disconnect it and then connect it straight up to the bulb. Starts off bright, gets dimmer and dimmer and dimmer. Okay. So we're just going to formalize that process of the bulb going on and getting dimmer and dimmer and dimmer. We're going to formalize it with graphs, which is what we're going to do now, and then we're going to look at some calculations that we can do as well. We've got a couple of graphs here. These are just time graphs of what happens over time. Voltage, I've got R. I'm going to rename that as B. Voltage through the bulb and current through the bulb. So when you saw that video connect this up, the bulb started off very bright, but then it got less and less bright. So this is, I'd say, well, it started off with lots of voltage, and it ended up, by the end, there was no brightness at all, so it ended up with nothing. This is the process I go through to make sure I get these graphs right. I go, I say it starts off high, ends up low. Now you could guess, what does that look like? Well, I just connect the dots. Right? Maybe some straight line like that. It turns out that's a good guess, but it's not exactly right. It turns out that in reality, if you connect this up to the right equipment to measure it properly, it's not a straight line, but it's a curved line, and it looks like this. And that curved line is exponential decay. Imagine my curve is drawn better than that. The current through is exactly the same. So we have electrons flow when you connect this up. They flow and they build up here. They're pushed away from this side. Electrons flow and they go around to the positive of the battery. They flow really quickly at the start, but as more and more electrons are built up over here, it's harder for more electrons to get on there. And so that current decreases. So it starts off high, ends up low. I go through that same process, and a nice exponential curve. The other graph I can draw is for the capacitor itself. So I'm just going to redraw this bulb one, exactly the same. The bulb starts off bright and then it went dim. I'm going to redraw that just for reference. The capacitor started off with nothing. It's just been connected up, nothing's going on there. So it starts off at 0, but after a long time, it's got lots of negatives here, lots of positive here. It's storing energy, and it's got a voltage. So after a time, it's got this. So the capacitor one looks the opposite, and that exponential looks like so. Discharging, remember discharging when we take the battery out and we just connect the capacitor up to the bulb. In the video, discharging was started off very bright, and then after a while it got dim. So voltage bulb starts off bright, ends up dim. So the same process again. Same graph for discharging over the bulb. The current, we had lots of electrons to start with, and then when we connected up, they flowed out. And then after a while, we get less and less electrons. So start with lots of current, less current at the end, or no current at the end. Exactly the same. The capacitor, last time the capacitor, when we charged, the capacitor looked like, the graph looked like this. So we'll just remember that. This is our bulb. Bulb starts off bright, goes to nothing. And the capacitor starts off with lots of charge and electric field there and ready to go. It starts off high, and after all that charge is gone, there's nothing left, no voltage left, and so that ends up low. So this was charging here of a capacitor, and this is just charging. If we look back, all the graphs are the same. They're all exponential decay except for charging the capacitor. That's the only one that's different. All of them are decay except for charging the capacitor. So remember I said we're going to look at graphs, and the other thing we're going to look at is just formalizing some sort of calculations. So let's think about charging. So there's my battery, a bulb, capacitor, and maybe a switch. There we go. When we connect the switch up and we start charging everything, remember the bulb, we'll change this to B. The bulb starts off high, ends up low. That's a nice one. And this one starts off low, the capacitor ends up charged. It turns out that when we look at these graphs, after a certain amount of time, let's say that time, in this case I'm making this time up, let's say it's 3 seconds. After 3 seconds, this is down to, it's lost 63%. i.e. it's only got 37% left. Now it turns out after another 3 seconds, so this will be here, it'll be 6 seconds, after 3 seconds, it's lost another 63%. And then we could do it, keep going, after this graph, keep going. After another 3 seconds to 9 seconds, it would lose another 63% again. You have to remember the 63%. You have to remember that. I'll explain where it comes from, but you don't need to know where it comes from. It comes from the fact that these are, remember this is exponential decay. An exponential decay looks something like, the actual formula for it is negative because it's a decay. I think it's something like that. This is e to the power of negative something. Effectively, if you do this on your calculator, if you do e to the power of -1 on your calculator, and you work that out, it equals 0.37, which is your 37%, which 37% is the same as 37% left, is the same as 63% lost. So it comes from this on your calculator. You don't need to know where it comes from. You need to remember that it is 63%. The same thing happens if you're charging a capacitor and that graph is growing. After that, whatever time it is, and in this case, I've told you it's 3 seconds. You could have another circuit where it's different. It could be a minute or something like that. This time, we have a name, is called the time constant. That's why this is the time constant formula. It's got a funny T. It's the Greek letter tau. It's kind of a curvy T. In this case, the time constant is 3 seconds. After 3 seconds, we've grown, you guessed it, 63% of whatever our maximum value is. After another time constant, in this case it's 3 seconds again, we've grown 63% of what's left. And then another time constant, 63% and 63%. So because it's exponential, it never actually gets there. But you can say, and you need to remember this as well, after 5 time constants, you're basically finished. You're so close to 100%, it's not funny. 5 time constants, you're finished. The other thing you get given in the formula sheet is that this time constant, I've set 3 seconds for my circuit. It depends on what's in the circuit. And what it is it depends on the resistor and the capacitor. So resistance time capacitor. So in this case, this is the bulb with the resistor and capacitor is the capacitor. You'll have values for that, I don't know, 40 ohms or something, and capacitance will be some value as well. They can find out the time constant. So we'll go through an example in the next video.